Hello everyone, February 21st. A little bit late as I work a little bit more today again, but it's all right. I just feel a little bit tired. We'll see how it goes. Recover a tree from pre-ordered traversal. I feel like I've done something like this before. We're going to pre-order DFS on a tree. At each node in this traversal, we output D dashes, where D is the depth of this node. And then we output the value of the node. If the depth of a node is D, the depth of its immediate child is D plus 1. The depth of the root is 0. We output D number of dashes. I think that's what it means. D number of dashes. If a node has only one child, the child is guaranteed to be the left child. Given the output traversal of this traversal, recover the tree and then return its root. Wait, what's a pre-order? I forgot. I forgot. I never remember these terms. What's a pre-order traversal? Pre-order traversal follows a root left-right policy. Okay, root left-right. So root left-right. So I go 1. Hold on. I'm just gonna try to write it out, draw it out. So I have 1 left. So we output dashes. So 1 dash to 2, 2 dash to 3, and 2 dash to 4, 1 dash to 5, 2 dash to 6, and 2 dash to 7. Right? 1, 2 dash 3 dash 4 dash 5 dash 6. Oh yeah, that's how it goes. Okay. So we start with a root. And then we'll move on. Basically, we just count how many dashes until we hit another number. The depth. Oh, not really depth. It's the value. So we have to parse the string, right? Maybe we should parse the string first. We parse the string such that what we're gonna get is the depth of each node, right? So depth 0, basically we have 1, and then depth 1 we have 2, depth 2 we have 3, and depth 2 we have 4, depth 1 we have 5. Put it here. We have 5, and then depth 2 we also have 3, 4, 6, 7. But if we extract it, we lose the information of the pre-order, right? So basically we start from 1, okay, and then we check. It's guaranteed to be the left child. So now we see, unless we don't have, there will always be left child. It will not be a right child. So it will always be a left child. So I count the next, and it will always be 1, right? Always be 1 dash. So we just count how many dash there are until we hit a number. So we have 1. So we say, okay, whatever the next is gonna be the child. So we start parse the number. So we get, okay, it's 2, right? And that's that. And then we need to check the next count. So the next count, if the same, then we'll go there. But if it's not, if it's +1, then we just keep going. I got 3. Next 4 is the same. The next is just 1, so I have to return. And I need to check if it's the same. If it's not the same, then I'll keep return until we hit a level, right? Until we hit a level where it's the same. So we got 5. Next, it's bigger, right? Bigger was always going here. Bigger is always, if you have the current level, and the next you find is bigger than the current, that's always going to be a left subtree. And if after you've done the left subtree, you check the next, right? You check the next. If it's the same, that will be the right subtree, right? And then you keep going. If it's bigger, then it will be your right subtrees next. I should go there. Oh, no, I think you should just keep going. Right, you should keep going. So you do 6, right? You just keep going. You go to 6, and here we expect to be 3, right? We expect the next to be 3, and then we count as 2, so we return. Right, we count as 2, so we return, and right, this is the current. We have the index, and I have the current depth, right? The depth count. So the depth count should be 3 for you to do here, but no. So we come back, and then yeah, you finish, and then we'll just check if it's the same. Then we go here. If it's not the same, then we just return. Right? If it's smaller than the current, then just return. If it's equal, then we do the right subtree. Then we do the right. Okay. And once it's done, I'll just return. Right? Because after you fill the right is a binary tree. So at each node, I know the index, right? I know the index. Maybe it'd be easier to parse it first, but we do it like this. You know, the depth value, depth value, depth value, right? We do a depth and value. Then we build. Now we have the actual number, so it'd be easier. So we just need to keep track of the index, right? We just keep track of the hardware and index this, right? And then we always add index the first one. We always add the first one, and then we say we'll call build, provide a node, and the index, the unknown index so far. If it's one larger than the current depth, then we do it, right? We create it, we call it. This one move down. And if it's one more, then we keep moving down. And if it's one move down, and then if it's smaller, then we just return. Right? The smaller we just return, And yeah, index, I think make it global will be easier to handle. We just return, and then once we return, we'll just check, right? Because we unwind and we basically just check. If it's smaller, then we just keep return. If it's equal, then we will do. Okay, so basically the problem boils down to two things. First, we need to parse the original string. So the parse itself feels like not that straightforward. Alright. What I think is let's do a private. Do an index. Okay. And then we need to parse the original string. Alright, how do I use pair then? Utility. No. I have no idea. Alright, let's keep going. Pair of what? Pair, this is gonna be parsed. Okay. Then we'll say int dash count. Okay. And for int I0 smaller than traversal dot size. Actually, no. Oh, let me think, because I all keep looping inside. I think it's better to use. Oh Jesus! It's better to use a while loop. Okay. If okay, how to check? Is digit. Is a function called is digit? Is digit. Yep. std is digit. Oh. What do you see type? Down. Yep. C type. So is digit traversal I, right? If it is digit, oh, we can say while it's digit, right? While it's digit that we've built up, right? We build up, and then once it gets out, then while it's this, then we build up. Once we build up this, 2 while loops. Interesting, very interesting idea. Let's do it. So we have dash count, right? And we'll have depth, right? So we say I smaller than traversal dot size, and right, while this, actually I want to do while, right, while this, ooh, I need to do the other one first, but it's fine. Essentially we say, because we have a digit, then we say depth equals depth times 10 plus traversal I minus a, minus a 0, right? And then I plus plus. Try the next one until we break out, right? And then before that we have to do another one. So it's very similar. Dot size, and this one is just traversal I is equal to a dash, right? If that's true, then we'll say dash count plus, and we need to move the I forward, right? Dash count this plus plus. And if it's still a dash, then we keep dash count, keep dash count, keep dash count. And once it's done, we'll get all the numbers. Once the number is done, then we finish the current iteration. Then what we do is we say parsed dot pushback, and it's gonna be depth and no, dash count is depth. Jeez, man. It's depth and node val, call it val. Okay, so this is depth, this is val. Okay, and then we'll push depth and val. Let's make a note. Each element is depth and val. We start with 0, so this is good. And then once we push it in, then depth we reset to 0, and val reset to 0. Right? Because at the beginning we don't have a dash, so this one doesn't do, and then we just basically go through all of this until no, it's not a digit, right? And then I'll push it back, the current, reset them, and then we go for the next. Okay, and then at the end it will be, yeah, plus plus will hit. I will be too big. Okay, yeah, so this build up the parsed, right? We have the depth and the val. So next we're just gonna build, right? We're gonna call a function. Let's say call it recover. new tree node val is going to be parsed 0, 1, right? Oh, parse 0 dot second. Okay, so basically we get a second, which is the val for the root. Okay, and then what we're gonna do is we will call build. So build will pass the tree node, and the index. Maybe I don't even need. I can just put index as 1, right? Index for the vector. Okay. Oh, sorry, I was brain farting. Come on, it's late. Okay, so this is the main thing, right? So what I'm saying is I don't think we need this anymore. Because we have index. This is current index. So, depth. We do need depth. The depth of the current node, right? Okay, so the next node is that. And if, let's say, index is equal to parse the dot size, that means we have handled everything. Then I think that just return. If it's not, then we have the node that we wanted, so we know the node current. Now we're dealing with my node, right? And we have the next node. So next node or next depth. Next depth shall equal to parsed index dot first. Next val is parsed index second. Okay, so we get a next depth of a next val. We have the current depth of the current val, right? Good. So, then what? Then we say if next depth is larger than the current depth. Because we're doing the index. right? I mean, of course it's going to be bigger. Oh, I'm not sure. If it's bigger, right, then in its first time, yep, if it's bigger, it won't be the same, will it? The current depth, right? The current depth. If it's the same, then we have to go back up. Okay. So if the next depth is larger than the current depth, then we say node left shall equal to new tree node next eval, right? We basically have a next node on the left hand side, and once I do that, and I'll say build node left, so build on the left depth is gonna be the next depth, right? It's basically the next depth. Index plus 1, because I'm handling this, now I need to move on to the next one, right? Index plus 1. I need to return something. Return the current index. Right, basically we'll return the index of that it can now work. So yeah, this one just build. So we build, we go to next, and the index plus 1, we have the next one target, and then we'll try, right? We'll try, and if it failed, and we have something, we're done. So the next one is the next index has given me a smaller one. Then I need to know what this next is. So maybe I shouldn't do void. Maybe it should be int. Right, is the next index. We call build. And then we'll get the next index. So we'll return the next index. I think this should just return index. Right. And this one will return next index. So int next ni equal to this. If ni is equal to parsed dot size, return ni. So this is a success. We already finished. If not, the ni points to something. Right? If not, then ni pointing to something. Then what? Ni pointing to basically that node cannot keep falling to the left. So now it turns back, and I need to check its depth. It made me feel like I really shouldn't. I think I should just do it this way. Parsed index first, right? And then this is parsed index second. So I save this line. Parsed index first, right? It's this depth. Here is we have something, right? And then we just need to check if the next is also, would it be equal to? Huh. If it's equal to, right? If the new index's depth is larger than the current depth, then that's the right. If it's smaller or equal to, then we need to return back. So we say if parsed next index of first is larger than the current depth, then node right new tree node parsed next index of second and int next I shall equal to build node right parsed next index of first next index plus 1 parsed. Okay, again, if next is equal to parsed dot size, or return next I. Otherwise, so basically this one will return something, but we return something the current already handled, so we actually doesn't really matter, we always return regardless of what this one, we will always return, right? Because we handle the left and the right, so we always return. Okay, so this is we're done with this situation, and I have else. Else is the parsed index. So the current node, the depth is smaller or equal to. So you're not supposed to be at this position. So we simply return index. We should return index. And well, I think we can just do it this way. Right? Or we can say, or parsed index of first is smaller or equal to depth. Then we just return this. Then we don't even need this. Right, so if it's equal to, or if then the index, it's the depth is smaller, so the next one is smaller or equal to the current depth, that means it will have to go to my parent. So we just return it. Otherwise, we set the left node, we get the next one, and then we get the next I, and then it's the same thing here, right? If the next is equal to or parsed next I of first small equal to depth, right? So after we build this, then we get the next, whatever next that we need to do. And if the next is already at the end, so you just return it. Or if its depth is smaller equal to the current depth, you cannot do. So you do that. And we are left with this. This is the other situation. Okay, so this is build. So we'll start with the root depth. The root depth, right? The root depth is actually 0. And index is 1. Okay, so node, current node, the node that's being visited now, the node that is being visited now, depth, the depth of the current node, index, the index pointing to the next available depth node pair. And of course we have parsed, a list of parsed depth node pair, node value, value. I'm actually not very confident, but I decided just put it out there. 1, 2, 8. First, parse traversal to get the order of the vowels and the depth, right? The depth, the order and depth of the vowels of nodes, then reconstruct. Alright, let's see if this one works. And if it doesn't, I'm actually going to bed. I feel like I'm suspending. I'm kind of being suspended at the moment. Looks okay. Let's just submit it. I don't really care. Alright, that's good. One of the easier, definitely, hard problem that I've ever solved. So the parse take on time. I just say the length of traversal is on. And the traversal itself, because each node gets visited only once, so yeah, it's just on. I think 0 millisecond. Oh yeah, it's just like a tree. It is a tree. Recursive string manipulation. I mean, what else can you do? A single pass with stack. No, I'm not doing that. With list. Yeah, I prefer first convert it into the this list. It makes it much simpler, right? It makes it much simpler. Good for you, 450 days. Good for you. Okay, that will be it. It's not that hard, but it's interesting. All right, now I can end this and go to bed. I still have to wash the dishes. All right, I'll see you guys tomorrow.